I've always found piecewise functions to be very interesting. You know, it's one of those things where how many pieces does it have, and what is each piece doing? And then yesterday we had this one, which was just two pieces. That's it. You know, that would be your basic piecewise function because it has the two pieces. But looking at B, we see this one's going to be broken up into three different pieces. And again, that all comes from right here. Seeing that? You know what? I'm going to close these import files because this is really slow this morning. Which tells me it's not liking that all of this stuff is open. Alrighty. So, graph the following piecewise functions, state the domain, classify any discontinuities, verify by graphing on the calculator, and in fact, I might also talk a little bit about the range as we go through these. Yeah. Yesterday we talked about, did you watch the video?
No,
We'll do that as we go through it. As I told everybody yesterday on the video, I'm going to go a little slower because it seemed like a lot of people did not necessarily remember piecewise. But again, the whole thing is, it's not necessarily difficult at the Algebra 2 level. And so things that are too easy for us tend to go right out of our brain. It's like, you know, this was supposed to be hard, but it wasn't, so I don't need to remember that. So what we're seeing here is that there's definitely a change going on over here where we have 0. So x is less than 0, something's happening. X equals 0, something is happening. And x is greater than 0, something is happening. So this is much like yesterday's in that what I want to remember is stuff is changing from one side to another of the y-axis. And so what I do is I put in this little helper line saying, hey, I've got to watch out. Something's going to happen over here on the left. And with this one, something's going to happen right at x equals 0. And then something else is going to happen over here where x is greater than 0. And so what we do is we figure out, well, where should this stuff go? Well, this top line is supposed to be used when x is less than 0. That's where we have -1, -2, -3, etc. So that's over here. Now notice I put the conditional with it. And that's because of the second piece of this. Once we graph x minus 1, we have to know whether or not we should put that at x equals 0. And then I notice the middle piece here is just at x equals 0, I'm supposed to graph 1. Well, I might go ahead and get that out of the way right now. Change colors there. And just put, I've got it 1. That's basic. And then on the other side, when x is greater than 0, x squared. So, usually I'll just do these left to right. And again, we notice this is very similar to yesterday's in that when x is less than 0, we're supposed to graph the line x minus 1. So we go down to -1, and just like yesterday, we realize, well, I can't graph it to the right. I would love to go up 1 and over 1 because that's the slope, but what I'll do is I'll use the slope backwards and go left 1 and down 1, and left 1 and down 1, which again would be -1 over -1, which is +1. So this portion of the graph, as we go to the left forever, because this is for x is less than 0, it's going to look like that. And then I stop, and I think, so should I include this point on this line at 0? And the answer this time is no. This does not have an equals bar. So I need to overemphasize that this would be an open dot at that point. It is not included at that 0 location. Because, as we graphed before, when x equals 0, boom, got it 1. That's where it is. Now I have to switch gears and think what's going on the right-hand side. And when x is greater than 0, I'm supposed to graph that parent function for quadratics, which is x squared. Basic parabola in your head, you can just quick say, if I put 0 in there, I'm going to get 0. If I put 1 in, I'll get 1. If I put 2 in, I get 4. 3 in, I get 9. So it's 0, 0, 1, 1, 2, 4, 3, 9. And we've got to connect those up into half of a parabola. And then we stop and think, at 0, should I be including my blue graph? And the answer is no, that does not have an equals bar. So that's why it's called a piecewise function. We really had 3 pieces that we had to graph of this function. And now it says we are supposed to state the domain and classify any discontinuities. So the domain of F, we take a look at it and we realize, well, we're using all the negatives for x minus 1, and we're using x equals 0. We graph that at 1, and we're using all the positives over here. So this is one of those situations where we're using everything for the domain. Right there. And I know it said verify by graphing on the calculator, but like I told you yesterday, that's not something you want to learn. You'll remember it for 2 minutes and then it'll be gone because it's much easier to graph these by hand. Now, the interesting part of this would be if we look at, oh, we have to classify the discontinuities. So we take a look here. And initially, we would probably want to say that the discontinuity there is as a whole. But there is a jump because this is from -1 up to 0 and from 0 up to 1. So this is actually a jump discontinuity. We can't just fill in one hole and this graph will be a function that's continuous. It's not going to look that way. And then, like I said, I do want to touch on range. This is a really interesting one, range. So my range is about my y's, and I think, well, this arrow is going down forever. So definitely going to negative infinity. But also a definite jump spot right here. You know, we were at -1, and then it made a jump. So we have to tell people that. -1, and we couldn't use -1. Remember, this did not have an equals bar, so that means we have to have parentheses here. Union with, and then I look up here and I say, well, it kind of started this graph at 0, but again, it didn't have an equals bar, so I'm going to have to tell people, all right, you can use 0 there. But then I also realize it's got this point of 1 sitting right here. So it's like, well, how do I start with 0 when that 1 is in the way? So I would probably go ahead and put that point 1 right here, even though it seems kind of out of line with the 0, because at 0, we had to graph 1. And then tell people, all right, the rest of it, we're starting at y is 0, but we can't use 0 because this did not have an equals bar, and then everything up above. So what we're doing is we're representing every single y that would be used for this graph. This was all used. So that was our negative infinity to -1. At 0, we had to graph y equals 1 right there. And then this portion of the graph went from 0 to infinity. Grace. Because we just had, if you look at the second line, this was the interesting thing about this one, Grace. Right there. Seems really out of place, and it is out of place because it was a really unusual piece to our piecewise function. It said, if you go to x equals 0, we're going to tell you just make a dot at y equals 1. So we have to include it. Now, you could do this backwards. You could put the 0 to infinity right here and put the 1 at the end. But because y equals 1 on this graph, we at some point have to tell them we graphed a y equals 1. So the order wouldn't be important here. It would be more about making sure that they know that had to be graphed. Because remember, the y's are about looking at the graph this way. And we can see our definite cutoffs here for our y's when we do that. And we have some we're not using. And if we have some we're not using, we have to leave those out. Yeah. Take care of it. Okay. Yeah. Piecewise. Very interesting graphs. Again, one of the things I talked about was using your calculator now when you're going through the homework so that all of those things we did in Algebra 2 start to come back to you. So that you remember, oh yeah, when it's x squared, I'm supposed to use 0, 0, 1, 1, 2, 4, 3, 9, you know, those type of things. They need to come back to you, and they will. It's just going to take a little time. So this one, you tell me, where should I put my helper one? It's at 0 again. Yeah, right here. There's my helper. should I use on the left-hand side of this graph? Top line or bottom line? X is less than or equal to 0. There's that x minus 1 again. So on the other side, just like so. Deja vu, here's that x minus 1 again. Well, we might just see it. All right, so x minus 1 down here. Again, we're going to use backward slope, left 1 and down 1. And then we figure out whether or not we should put an open or closed dot right there at 0. What should we do? Close this time? So again, I know it's hard to overemphasize a dot, but we need to do that so that I can see, hey, that one's included. So now I look at this one, x squared minus 1, and I think, well, that's my normal parabola that I was doing before, shifted down 1 unit. So it started at 0, 0 before. If I shift that down, that's going to be at, oh, look at that, 0, negative 1. Start there. And then I would normally get 1, 1, but I remember now I have to subtract 1, so 1, 0 will be a point that I could get. And normally I would get 2, 4, but now it's going to be 2, 3, because I have to move it down 1. 3, 9 will become 3, 8. Connect it up. And now, you look at that graph, and this is what Hannah was asking. What if you have an open dot and a closed dot? Well, it's a good thing I did this in 2 colors then, because now I can clearly see, hey, whoever graphed this understands that this one was supposed to be included while this one was not. But basically, if you're using pencil on your test, as long as there's a big dot there, you're okay. Because I will know that you understood that one of them was included at that point. Yes. Okay, let's not do that, because then you're not bringing that graph together. And this example explicitly was for that. So we can see that sometimes they come together. Sometimes there aren't any discounts. Even with piecewise functions, sometimes there won't be discounts.
It's just like, it's one function of piecewise. Well, it's not one function, but it's meant to be one graph. But it well, what do you do?
That's the thing. That's why I said the colors are helpful here. Because this way you can tell, hey, the green one, that's supposed to be included and the blue one's not. But on your test, as long as there's a dot there and it's filled in, you're okay. Because I'll be able to see that. No, you'll be perfectly fine. So this one does connect up, but that's the big deal about this one. So domain of this one. And this was F again. What's our domain? All reals. Forever. What's our range in this one? It is. It's all reals. This one connected up. So we were okay. Any discontinuities? Not a one. So this one is continuous. Oops, I better spell continuous right. And yeah, some of you had the leadership academy thing you had to go through today. So I'm going to be recording. So whenever you have to go. Yes, because if any portion of this piecewise function fills that hole, then it's considered continuous. And we can go through it and just not lift our pencil up. Now, obviously, when we graphed this, we had to lift our pencil because we knew, hey, this is one portion of the graph and this is another. But when you're done, if you can take your pencil and you can graph over the whole thing without lifting up your pencil, it's a continuous function. It will look exactly the same. And that's what makes these a little bit harder to grade, because it's did they understand which one was supposed to get it or not. But you know what, in the end it doesn't matter. As long as the hole is filled, that was the intention of the problem, was to fill that hole. So however you need to do it, you do it. Yeah. All right. Piecewise functions. 4, 3, 2, 1, 0. So this tells me maybe I need to tell Algebra 2 to spend maybe 4 days on piecewise functions instead of just 2. Some. Alrighty, so off to something else. We've got.
Please excuse the interruption. All sophomores that received a Leadership Academy invite, please report to the comments at this time. All Leadership Academy sophomores, please report to the comments at this time.
We have a much more basic concept now to talk about. And that concept is whether or not functions are increasing or decreasing. And all you want to ask yourself is, what's happening to my y's as I graph this from left to right? And that's how we read anything, is from left to right. So as I graph this function, my pen is constantly moving up. Now you might say at some points it's moving up really, really slowly, but it's not.
What would a sine graph be?
Sine graphs and cosine graphs,
Yeah.
you're going to have to hang on to those. Those are nice waves. Those are sound waves. So we'll get to those, but that's part of our training. So this one is definitely increasing. Now they're also going to ask us about over an interval, whether or not something is increasing or decreasing. So that means what they want you to do is basically just look at a certain part of the graph. Like, let's just say they asked us whether or not this is increasing over the interval from -3 to 3. Then what you do is you try to ignore anything that's to the left of -3 and anything that's to the right of it, and just look at the middle portion of the graph. This is still increasing over that interval. So that's an increasing function. This one, again, it may seem like it's not moving down a whole lot, but it is constantly moving down in that function. So that would be a decreasing function. And then any horizontal lines that we see, those are considered constants. So they're just going to ask us whether or not for this interval, is it increasing, is it decreasing, is it constant, what do you see? Which for normal functions, things like this that we see, seems pretty doggone basic. You're just looking to see, are we going up, are we going down, are we at a horizontal line? So the increasing, decreasing, and constant function on an interval, function f, is increasing on an interval if, for any 2 points in the interval, a positive change in x results in a positive change in f of x, which is y. That just means the slope is positive. Now, if you have a positive slope for the portion of the graph that you're looking at, it's increasing. If, however, you have a negative slope over that interval, then we're looking at decreasing. Cameron, it goes. Pay attention. And then, if we have horizontal, we're talking about a constant. So a function f is constant on an interval. For any 2 points in the interval where a positive change in x results in a 0 change in f of x. And the slope of any horizontal line is going to be 0. So we can tell by those slopes as we go through it. But the equations themselves sometimes don't indicate that slope to us, especially if we're talking about hyperbolas. So to start off with, we're going to graph them and take a peek and say, okay, what's going on here? So this says what we want to do is look at this very interesting little piece of graph over here, and it is a function. And we want to see where's it increasing, where's it decreasing, and all of that. Now this would be a piecewise. There's definitely something different going on here than here and here. So this would be a piecewise function. But one of the things that we need to know is that the book is absolutely wrong on the way it does the interval functions for some of this homework. When you look, and I don't want you looking at the back of the book for answers, remember, they use closed brackets. And that makes absolutely no sense, because an interval is not a point. They're not the same thing. We went to Mrs. LaRue when we saw this in the book, and we're like, this is wrong. What are they doing here? And she said, absolutely don't teach it that way. So they are all over the place on this. Use my answer sheets. Don't use what they have. So state the intervals on which the graph is increasing, decreasing, or constant. We will never use square brackets ever when we are talking about an So for this one, well, this is decreasing, it's going down. So the first thing I see as I read this graph from left to right is that I'm going to have a decreasing interval. And again, your book doesn't put the arrows there, and that's actually a very big deal, because we want to say that this is negative infinity to negative 2. That's where it's decreasing. It's going down from left to right. Yeah. Because a number of points cannot be an interval. An individual point is never an interval. An interval tells you from here to here. So it doesn't make sense to have any square brackets on intervals. So just know whenever you do any interval notation, you should never be using square brackets. Ever. Then this middle portion is definitely constant. So I think, well, what numbers match that interval? And that would be from negative 2 to 2. And then we have an increasing piece to this function. And that's definitely from 2 to infinity. Looks like so. So we will never use square brackets for intervals. Because that makes no sense. A point is not an interval. Yeah.
So because like negative 2 and then decreasing is also included in the
Is it included?
well, like, it's also like a part of, you know what I'm trying to say?
I know what you're trying to say, but you're overthinking this. Because all we want to do is say, this is going forever, it cuts off at negative 2. So just think of it as a cutoff. Where's the cutoff for this interval? Negative 2 to 2, cutoff. 2 to infinity, cutoff. And infinity doesn't have a cutoff, but you know what I mean. We're looking for just kind of an endpoint on a graph to explain it.
What if they're like closed dots?
Not good. So we're going to talk about functions. And so it's very rare that we talk about this along with what we had for those other graphs that we were doing with closed dots. Usually they're continuous graphs that we talk about these ones. So down here in this little box, it just says exactly what we have over here. But again, this is a big no-no. No square brackets. So I almost hate to uncover that. Do not include those square brackets in any intervals. So next up, analyzing a function for that increasing and decreasing behavior. Well, they're not always going to give us the picture. Sometimes we have to get the picture ourselves. The good news is we know what this is going to look like because we did lots and lots of that last year. So I don't want to grab a graphing calculator for this one because I'm pretty sure with just a sketch we can talk about increasing and decreasing. So I look at this and I realize, okay, this 2 business is connected to my X. That tells me a right and left shift. And right and left shifts always work backwards from what we think they should. So this says +2. That's actually telling me my graph is going to go 2 to the left. So I'm going to have to go 2 to the left and graph my parent parabola. Right there. And that's really all I needed to know in order to figure out the intervals of increasing and decreasing. So over here, I think if I were just reading this graph, I am definitely going down from here to here. So that would be a decreasing interval. C in there. So what should I use in my parentheses for decreasing? Negative infinity to negative 2. Oops. Started to write 2. My hand's not keeping up with my brain this morning. That's not good. There we go. What do you think about the right side of this graph? Increasing. Over what interval? Negative 2 to infinity. Now, if you're thinking there's no way I would have remembered that that's my parent function, x squared, 2 to the left, you've got a graphing calculator. calculator, graph them for a while, and it'll come back to you. It will. And we'll also be reviewing this stuff as we go through it. Now for B, oh golly, that we probably don't remember. That's our hyperbolas. But we do remember what we did yesterday, which is if that x plus 1 and that x minus 1 in factored form are not going to cancel out with our numerator, those are asymptotes. Those are vertical asymptotes. So we would have our x and y axis, and we would have asymptotes at -1 and 1. And if we wanted to do this by hand, we would put in some numbers that are bigger than 1 and see what we get. We would put in 0 and maybe a couple of fractions like 1/2 and -1/2, bless you. See what we have in there, bless you. And then we would also take a peek over here after -1, so -2, -3. But because what we're focusing on right now is increasing or decreasing, we're going to slap this in the graphing calculator. Just make sure that you use parentheses for your denominator. Because we need to let the calculator know that we're going to divide by everything that we're plugging in here. And I'm going to do zoom 6 to get this back to -10. And that fits fantastically with what we know about our asymptotes. So if we could go back and make a sketch based on what we saw there. I better switch colors here. And like I said, what we're focused on is decreasing versus increasing versus constant. So we don't necessarily need a perfect graph of what this is. So take a look at the first thing that we hit, the first portion of the graph as we go from left to right. Is this piece, this red piece here, increasing, decreasing, constant? What's happening? It is increasing. It's going to go up. So we've got an increasing from where to where? -infinity to -1. All right. Middle portion. As you read this from left to right, at first it's going up, right? So we could include that on our increasing. So we could also do increasing from -1 to, where's that change over? When do you stop graphing upwards for that middle portion? It's 0. Because as we go from left to right, it's that 0 right there. And then I think, well, now it goes from increasing and it switches over to decreasing because now I'm graphing down. Over what is it? 0 to 1. Now we just have to figure out that other branch. From left to right, what is this one doing? Definitely decreasing. And what interval? 1 to where? It is infinity. And at some point, it will almost look to us with the naked eye as if it were constant. But we know the math says it's going to keep getting closer and closer and closer to 0 because we understand things like fractions, where if you have 1/2 and you cut it in half, you get 1/4. Then you get 1/8. Keep cutting it in half and you will never be able to stop. So it is infinitely going down. It's just, it's going to kind of look like a constant because our eyes won't be able to see the difference. So that is going to be interval talk. 4, 3, 2, 1, 0 me on increasing and decreasing. Good. All right, so let's go on to another fairly basic topic. That's just something that you never talked about in Algebra 2, and that is boundedness. To be bounded means that there's some horizontal line that you can draw that the graph is never going to touch. Whether or not it's above it or below it, or if it's both, then the entire graph is considered bounded. So we can say bounded above if there's a cutoff that it will never get to above our horizontal line. And we can say bounded below if there's a cutoff below it. And then if it's both, we just call it flat out bounded. So this one says it's not bounded above and it's not bounded below, which is really hard to tell without the arrows. But that's what the arrows tell us. This is going up forever. We're never going to be able to draw a horizontal line and this graph is not going to cross. Same thing down here. We're never going to be able to draw a horizontal line and this graph isn't going to cross.
So can you just call this unbounded? Or do you have to specify that's unbounded?
You know, we just don't generally even say that, but if it asks for boundedness and you want to make sure that I understand that you know it's not bounded, yeah, unbounded would be the best way. Then this little bugger here, that's going up forever. However, if I draw a horizontal line right there, this graph will never cross that. So that is bounded below. Then over here, and by the way, these would end up probably being cortex for these two. And that's because we see that parabolic nature. And if we look at the number of turning points, with there 1, 2, 3 of them, and we add 1, we would get a cortex. And then this one, arrows are showing, hey, we're going down forever. But we definitely draw a horizontal line up there that this is never going to touch, never going to cross. So that's boundedness. Now, we've got one more down here, which just happens to be both, and this is what we were talking about a little bit ago. And that's, if it's bounded above and it's bounded below, then you just say, hey, it's completely bounded. And that's what this one is. Because we could draw a horizontal line here. We could draw a horizontal line here. Never going to touch it. So there's always a worry because some students say, well, do we want them to touch or don't we? No, we want them to be like asymptotes, but they're not. We want them to act like asymptotes. Like it's something you're getting super close to that you're never going to touch. So bounded and unbounded. Now they're going to make this sound really complicated, but it's not. We already know that. A function f is bounded below if there's some number b that is less than or equal to every number in the range of f. Basically, it's saying if you have a cutoff for the range, then you're going to know. I'm not using anything below this or above it. So that would be considered what's called a lower bound, but we say it's bounded below. A function is bounded above if there's some number b that's greater than or equal to all of the graph down here. And like it says, we call that number b the upper bound if we can find it. Sometimes it's difficult to figure it out without the calculator.
If you had a graph that jumped, would you treat that as two separate graphs and say one is bounded above, one is bounded below?
That's where we talk about bounding over an interval, where we say, from negative infinity to 0, it's bounded below. From 0 to infinity, bounded above. So it can change if you look at it over an interval instead of looking at the entire graph. A function is just flat out bounded if it's bounded above and bounded below. So this one says we can extend the above definition, talking about boundedness here, and we want to extend that to the idea of bounded, what Adam was just asking about. If they just say, you know what, explain from here to here whether or not it's bounded. Give us certain x values that we're supposed to look for. So if we restrict that domain by looking for certain x's, in each part of the definition to the interval we wish to consider. So just this portion of the graph. For example, the function f of x equals 1 over x. All right, well, first off, we did this one yesterday, but it had a 2 on top of it. Give me the basic shape of that graph. What does it look like? It's a hyperbola. Yeah, we're going to have our 2 branches. And remember, it's going to go through 1, 1, and we can put a 2 in there real quick and get 1/2. But this is going to be really close in to the origin. start to feel right. So, just like Adam was talking about, here we have a graph, and it's not a piecewise. This is a hyperbola because they have those branches that we look at. We would have a different interval and a different boundedness for this one because we could say, if you don't look at the right branch of this hyperbola, that's gone. Okay, that left branch, that's bounded. It's bounded above. And if we just look at the right branch, that one's bounded below. So if we look at individual intervals, then we can talk about it. And then that's what they're mentioning here. From negative infinity to 0, we've got bounded above. And then from 0 to infinity, we've got bounded below. There's a cutoff there. So what they want us to do is to check for boundedness. Ooh, I see the recording is 36 minutes. All right, we're good. We should be able to look at this one. All right, identify each of these functions as bounded below, bounded above, or bounded. So they're not doing intervals with this. They're just saying take a look at it. So my hope is we can get a picture of this graph in our noggin. All right, so here's what I look at. It's x squared. It's going to be parabolic. It has a 3 in front. That's a vertical stretch factor of 3. So it's going to be a little skinnier than our normal x squared graph. But it also has a -4 in the back. And so that means that vertex is going to go down here to -4. So skinnier. And one down to -4.
I didn't know the vertex down at -4. It's not a vertex 4.
Our normal vertex for h and k in this formula is 0, 0. The only thing that's going to change that is moving this by translation right and left and up and down. So this a in front is just always responsible for vertical stretches or compressions. If it's a fraction between 0 and 1, it's a compression. If it's a number bigger than 1, then it's going to be a stretch. And I'm looking at this x and I'm saying to myself, there's nothing behind the x, so there would be parentheses to move that together. So it's not going to go right or left. But this k value in the back, that always indicates the up and down. So it's definitely going to go forward. What would you say about this graph for boundedness? Bounded below. Bounded below. B, some kind of hyperbola, right? I mean, that's what we would say, some kind of hyperbola. But beyond that, we're kind of stuck. The denominator is not factorable. So we don't have any vertical asymptotes to go by or anything. So with this one, let's just grab the calculator and see this weird little graph here. Let's see, we had just x up there. Divided by, parentheses 1 plus x squared. This is indeed a very weird graph. It really is. So, I look at that and I try to figure out boundedness. What is it? It's just plain bounded. It's bounded above and it's bounded below. And it looks like the cutoffs would be 1 and -1 for the lines. So make a little sketch here. Something goofy like that was happening. Bounded. Now, I'm going to show you the algebraic way to see this. But again, it's different with every type of graph that we go through. So this is something we're probably not going to test you on. But what we're going to do is just show it to you so you have some exposure to it. When I look at this graph, I immediately think my parent function is x squared. Definitely going to be an x squared. So what I want to know is, if it's bounded, my normal parent function, x squared, would be greater than or equal to 0. If it's because that would go through 0, 0. And what I'm going to do is I'm going to build this up so that it becomes 3x squared minus 4. Now, how do I do that? Well, I multiply both sides by 3. And get 3x squared is greater than or equal to 0. And then I need this to have a minus 4 on it, so I'm going to subtract 4 from both sides. And now I've verified algebraically that this does have a cutoff. The lowest point possible is negative 4. Nothing else is going to happen below that. So that's the verification. And you can use that method whenever you're doing quadratics. With cubics, it's not going to matter because cubics are always on the numbers, so they're never going to be bounded. But with quadratics, we will be able to use that method all the way through. That one is more of a problem. So x over 1 plus x squared. Now here's the thing. When we look at that, we should be saying to ourselves, it looked like it never got to 1. So x over 1 plus x squared looks like it's going to be, whoops, less than or equal to 1. So what I want to do is I want to do the math to see, does it ever really get to 1? So to do that, you can solve inequalities the same way we solved our equations, but just remember if they were multiplied or divided by negative, you have to flip the sign. So I could multiply both sides by 1 plus x squared. I'm going to put that on here for people that are gone. It'll look like that. And if I were going to solve it, I'd move everything over to one side. So 0 is less than or equal to x squared minus x plus 1. Now, if it's going to reach 1, we should be able to find an answer for that. If it's not going to reach 1, we're not going to be able to find an answer. So the first thing we would try would be factoring. So I guess we're looking for two numbers that multiply to 1 and add to negative 1. Not going to happen? Okay. So then I would start to wonder, well, maybe there isn't an answer to this. And that would bring me back to the discriminant. Because if there's not an answer, we are absolutely right. This was bounded above. So if the discriminant comes out to be negative, we know this has no real solutions. So this would be negative 1 squared minus 4 times 1 times 1. And that's going to be 1 minus 4, which is negative 3. And the negative discriminant tells us there are no real solutions to this. So we were right. This was bounded. So that's a different verification method because we're working with hyperbolas. We're generally not going to ask you to do that. We're just going to ask you to represent the graph and then tell us whether or not it's bounded above, bounded below, or just plain old bounded. So, we didn't get too far today. But you know what? I'm okay with that as long as you guys feel like you know what you're doing at this point. You know? So do you feel like you understand bounded above, bounded below, bounded? All right. Again, you're not going to be able to do the whole assignment. You can definitely, I think, finish up the second day now. But yeah, there's no way you'll be able to do all of those down there. We haven't talked about symmetry yet. And a lot of the end of this section is going to be about even and odd symmetry. You hung in there really well. I mean, we're really going in depth about these functions.
According to staff, at this time, we're asking all students to log into the Help Time software to verify your Help Time enrollment today. Please be certain to double check your location and the title of your session. And that's
Okay, and if you get your Chromebooks out, I need to see the green. Sorry.
show your green
I know,
background on
that's
your
what you
screen.
typically does.
Or teachers, so that they can confirm